It's a valid opinion, but I'm more of a
Doritos. Yeah, because you're the one that thinks that the taco in the bag.
I should figure that out, but just take them to.
Usually the chemistry for the walking taco.
Make it like a bonus question with those.
Oh, speaking of which, okay. Okay, so we're talking about pressure. So, we've been looking at the equilibrium constant in terms of concentrations. Yeah. I was going to do a thing. Now I don't feel like it. So I'm just gonna tell you what it is in terms of pressures. So this here, of course, is concentrations. You can use pressures so let's say we use this same equation here. It's still going to be products over reactants, only now let's see. Okay. So same idea, only you're using the partial pressures of all the gases in the system. And we do have to have a connection between, and so in this, you want to put a little subscript P on it. We do have to have a connection between K and KP. So your K is going to be your, in terms of concentrations, KP is in terms of pressures. Now you can only use KP if you have a system that's all gases, okay? So we need to ask ourselves, what is going to be the connection between K and KP? Okay, so let's use this general chemical equation here. We know that our K is going to look like that. Yeah. So then we go back to our ideal gas law. And out of all those figures there, how do you put that together to get concentration? What are the units of concentration? Moles per liter. So how do you put those together to get moles per liter? Liters is a what? It's a volume. So I have to have moles over volume. Okay, so if you move everything around in here, you're going to get N over V. It's going to be P over RT. Okay? So we can put this P over RT in the place of each concentration. Partial pressure of C over RT. Okay. Now, going to rely on how experienced you are with exponents. Because I can take those exponents in and have the numerators and denominators each raised to the same exponent. Okay. Now, who remembers how to separate this into two different, who remembers how to separate fractions, first off? Well, yeah, so if I have A times B, let's see, over C times D, you know that this can be A over C times B over D, right? Okay, so that's essentially what we're doing here. So we're going to separate out these partial pressures. And then we're going to have our 1 over RTs left. All right. Now this left fraction here, what is that? The partial pressures of products over reactants. This is our Kp value. And I'm going to multiply these two together. And I'm going to get, let's see, 1 over RTL times RTM. All righty. Because when I do this, now I have a single fraction in the numerator and a single fraction in the denominator. I'm going to do something and see if this makes sense to you. So this is going to give me Kp, and then on the top, I'm going to have RTJ, RTK. Did that transformation make sense? I essentially did, I have a fraction in the numerator, fraction in the denominator. I essentially did the flip and multiply twice. Now, from here, how can I turn each one of those, that numerator and that denominator, into a single expression? What happens with RTJ times RTK? Do RTJ plus K. All righty. And now I want to turn this into a single expression. So now I'm dividing two values that have exponents, so I subtract the exponents. So that's going to be RT J plus K minus L plus M. Okay, so K is going to equal that. However, if we want to get it to the way the book does it, if we divide through by the RT, you know that exponent gets a negative sign, right? So your book has KP by itself. So then we're going to have one, well, let's put K. And then I'm going to have RT. So like that, because I divided through, it's going to be K RT negative alrighty, which is just going to reverse those two. Yeah. And so this is going to give us L plus M minus J plus K. Your book calls this delta N. And that little n still means mole value. So you notice that the LM and JK are your coefficients. The LM are your coefficients from your products. Your JK are your coefficients from your reactants. Your delta N is you're going to add those coefficients together, then subtract them, and you're going to see what delta N becomes. Okay. This might make more sense. So there's your KP. I was going to do another derivation, but I'm not feeling super awesome, so we just skipped it. I was going to show you some very surface level physical chemistry, but hey, better off for you. Oh, you had to do with chemical potential and activity, but we'll just go straight with that's your KP. And then you want to make sure you have this relationship down. It might make more sense if we look at, say, an actual reaction, okay? So let me bring this reaction up here. Yeah, I don't need to use this in that reaction. So I'm going to say, let's say, I'm going to use the same reaction. So N2 is 3H2. Two and H3. So how do I connect the K and the KP? So I know that my K is going to be KP RT delta N. So I have to figure out what delta N is, okay? So you know that delta N is going to be the coefficients of your products added together, which in this case is just 2. You could also put 2 plus 0 because there's only one product, minus the coefficients of your reactants, 1 plus 3. And that's going to give you 2 minus 4 equals a minus 2. Okay. So in this case, for this reaction, your K would be KP RT to the minus 2, which of course you can leave it like that and just put that in your calculator. Or we also know that a negative exponent puts the quantity in the denominator. Okay, so that is your connection going from your equilibrium constant for concentration to pressure. Now, so here we have same reaction. It's all gases. And so you're told, well, let's see. So we have equilibrium pressures to start with. So, and then we have different pressures, and the question is this, is this second system in equilibrium? Okay, so the system we're actually studying is this one right here. And it's like, is this equilibrium? Okay. So let's check. So our KP, these are going to be our equilibrium pressures. So we have our pressure of N2 times our pressure of H2 cubed. Pressure of NH3 squared. So now I'm going to plug numbers in and see what I get. So my N2 is going to be 0.85. My H2 is 3.1 to the negative third cubed. My NH3 is 3.1. That's 10 to the negative second squared. And when you multiply this all up, you're going to get 3.8 times 10 to the fourth. Okay. Now, let's check this system with these different pressures. Now, you remember this could just be an equilibrium point. It might be, it might not be. So since we don't know exactly what point this reaction is at, we're not calculating K necessarily. We're going to calculate the reaction quotient Q, which is the exact same equation. Okay, so for the second set of pressures, I have 0.525, 0.00761 cubed, 0.0167 squared, and I'm going to get a reaction quotient of 1.21 times 10 to the third. Okay. So you can automatically tell this system is not at equilibrium. That second set of pressures does not reproduce the same equilibrium constant. Now, here in a little bit, you're going to know what to do with both Q and K to know which way a reaction is going to proceed. If Q equals K, you're at equilibrium. Which you see we're not here. Okay. So here, at 1100 Kelvin, your Kp is 0.25 for this reaction. What is the value of K? So we know that Kp connects to K through our RT delta N. We want to know K, so we're going to divide through. Okay, then we ask what delta N is going to be. Delta N. Okay, so our products, that's 2 minus our reactants, 2 plus 1. That's 2 minus 3 equal to negative 1. So this is going to be Kp RT to the negative 1. Now, you know what happens when you have a negative exponent. That puts this whole thing in the denominator. What happens when the negative exponent is in the denominator? Yeah, it just brings it back up. So this is going to be Kp RT. And so we're working with gas reactions. Which R do you think we're going to use? Well, so we've been using two values. We have the 0.08206 or the 8.314. Yeah, because that one has the proper units, the atmospheres, kelvins, moles, liters. Whereas remember, your 8.314 is for energy reactions because it has units of joules. So your K is going to be 0.25. Then your R is 0.08206. Liters times atmospheres, kelvins times moles. And then we have 1100 Kelvin, and we get a K of 23. So it's not too bad to get those to connect. You just have to figure out your delta N. An equilibrium constant. Remember, your equilibrium constants, your reaction quotients are not going to have units. Okay. Heterogeneous equilibria. So we've been dealing with the terms homogeneous and heterogeneous for a while. Same idea here. So if you look back up here, you see how everything's a gas? That's a homogeneous equilibrium. Heterogeneous equilibrium, you see how I have mixtures of solid and some gases? Well, we can. What, the equilibrium constant?
No, I think like solids and.
Oh, no. He's right. You do leave them out. Okay, I thought you were saying you couldn't use the equilibrium constant. No, we can. You're just going to leave the so what you're going to find out is the only values that go into an equilibrium constant are gases and aqueous materials. So if it's a liquid or a solid, you leave it out. And that's because its activity chemically is essentially 1. So wherever there's a concentration, would be a concentration of a solid or a liquid, you can just put a 1. So as you were saying, what we would expect if we didn't know that already would be what we'd have. However, this is a solid. And with its activity being essentially 1, also, if you don't want to think of it in terms of chemical activity, you could say that your concentrations of liquids and solids are not going to change during a reaction. Okay? So what you're going to get is your actual equilibrium constant is going to be that. You see how we left the solid carbon out of it? Yeah, we do. I did that backwards. No, it needs to be like this. Flip those. The whole point is you're leaving solids and liquids out. With this one in particular, we can actually use the KP because you see we have everything as a gas except for the solid carbon. So we could also have KP. So that also works in this case. Okay, so there's your rules. Your heterogeneous equilibria, your Ks do not depend on pure liquids or solids. So you just want to leave those out. So let's look at this one here. So we have a solid gas. Our K for this one So let's see, we'll leave that one out and that one out. So we would have O2 cubed. H2O squared, or UKP you could also use the pressure equilibrium. Okay, and so next time we meet, we'll start at reaction quotient.
It's just always has, like soothes my